Let yourself settle into this moment, into the comfort of wherever you are right now. Feel the weight of your body sinking gently into the surface beneath you, as though you're being cradled by the earth itself. Take a slow breath in through your nose, filling your lungs completely, and then release it gradually, letting any tension flow out with the air. With each breath, feel yourself drifting into a state of peaceful curiosity, ready to embark on a journey through the cosmos without ever having to move. Tonight, we're going to explore one of humanity's most extraordinary achievements, a story that unfolds at the very edge of our solar system, where two small spacecraft continue their lonely vigil in the darkness between the stars. This is a tale of discovery, of persistence, of machines that have outlived their designers' wildest dreams, still sending whispers of data across billions of miles of empty space. But more than that, it's a meditation on distance and time, on the human spirit that compels us to reach beyond what we can touch, to explore what we cannot see. Before we begin, if you're finding peace in these stories of science and space, I'd be grateful if you'd take a moment to subscribe to The Science Pillow and leave a like on this video. Your support helps me continue creating these journeys into the wonders of our universe, these gentle explorations designed to calm your mind and ease you into restful sleep. It means the world to me, and it helps this channel grow so that more people can find rest and wonder in the mysteries of the cosmos. Now, let's drift together into the story of the Voyager spacecraft and the astonishing discoveries they've made at the edge of everything we call home. The twin Voyagers begin their journey. Picture, if you will, the summer of 1977. The world was a different place then, filled with different concerns and dreams. In Pasadena, California, at NASA's Jet Propulsion Laboratory, engineers and scientists were putting the final touches on two identical spacecraft, each one roughly the size of a small car, bristling with instruments and antennae, like some exotic insect fashioned from metal and silicon. These were the Voyager probes, and they were about to embark on the longest journey any human-made object had ever attempted. The opportunity that prompted their creation was celestial in nature, a rare alignment of the outer planets that occurs only once every 176 years. Jupiter, Saturn, Uranus, and Neptune were positioned in such a way that a spacecraft could visit all four, using the gravity of each planet to slingshot itself toward the next, like a cosmic game of billiards played across billions of miles. This alignment, recognized by a graduate student named Gary Flandreau in 1965, opened a window for what NASA would call the Grand Tour of the Solar System. On August 20th, 1977, Voyager 2 lifted off from Cape Canaveral atop a Titan IIIe Centaur rocket, its engines carving a pillar of fire into the Florida sky. Despite its numerical designation, Voyager 2 actually launched first, following a slower trajectory that would allow it to visit all four giant planets. 16 days later, on September 5th, Voyager 1 followed, taking a faster route that would get it to Jupiter and Saturn ahead of its twin, though it would visit only those two worlds before heading out of the plane of the solar system entirely. Each Voyager spacecraft was a masterpiece of 1970s engineering. At their hearts sat computer systems with less processing power than a modern digital watch, yet programmed with enough intelligence to navigate the hazards of space and make decisions when the delay in communications with Earth, stretching to hours, made real-time control impossible. The spacecraft carried 11 scientific instruments between them, designed to study magnetic fields, charged particles, plasma waves, cosmic rays, and to capture images and spectra of the planets and their moons. But perhaps the most poignant feature of each Voyager was something that had nothing to do with science, at least not in the conventional sense. Mounted on the side of each spacecraft was a golden phonograph record, 12 inches in diameter, plated with gold and enclosed in an aluminum jacket. This was the Voyager Golden Record, and it represented something extraordinary, a message from humanity to any civilization that might one day encounter these vessels drifting through interstellar space. The creation of the Golden Record was spearheaded by a committee chaired by the astronomer Carl Sagan, who understood that the Voyagers would become, in essence, ambassadors for Earth, carrying a piece of our world into realms we might never reach ourselves. Sagan and his team, including his future wife Anne Druyan, the writer Timothy Ferris, the artist John Lomberg, and others, faced a challenge both profound and humbling. How do you represent an entire world, an entire species, in the limited space available on a phonograph record? Working under intense time pressure, with only months to complete the selection and production, they curated 115 images that attempted to show what Earth is like. There were photographs of landscapes, from deserts to forests to oceans, images of human anatomy and human activities, pictures of animals and plants, diagrams explaining our location in the galaxy and our understanding of mathematics and physics. They included the structure of DNA, images of human conception and birth, photographs of people from different cultures engaged in everyday activities like eating and learning. To these images, they added sounds. Natural sounds like thunder rolling across the sky, wind rustling through trees, waves breaking on shores, and the songs of birds and whales. They recorded human sounds too, footsteps, heartbeats, laughter, the cry of a baby, and, crucially, they included spoken greetings in 55 languages, from ancient Akkadian spoken 6,000 years ago in Sumer, to modern tongues like Mandarin, English, and Wu dialect. Each greeting was brief, often simply saying hello, or peace, or greetings to you, whoever you are. The committee agonized over the musical selections, trying to represent the diversity of human culture and emotion in just 90 minutes of audio. They chose Bach's Brandenburg Concerto, Beethoven's Fifth Symphony, Mozart, Stravinsky. They included Chuck Berry's Johnny B. Goode, blues and jazz, music from Java, from India, from the Solomon Islands, from Peru, from Zaire. Each selection was chosen not just for its beauty, but for what it might communicate about the human experience. President Jimmy Carter contributed a written message, encoded as an image on the record. Part of it reads, "This is a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope and our determination, and our goodwill in a vast and awesome universe." The record's cover was carefully designed with diagrams explaining how to play it, including a stylus attached to the aluminum jacket. The cover showed Earth's location relative to 14 pulsars, cosmic lighthouses that could serve as a map for anyone trying to trace the record's origin. It included a piece of uranium-238, whose decay rate would allow any finder to determine how long ago the Voyagers were launched. But the Golden Record was more than just a message to aliens. As Sagan wrote, The launching of this message into the cosmic ocean said something hopeful about life on Earth. It was a gesture of optimism, a belief that despite our flaws and conflicts, humanity was capable of looking outward with wonder, of reaching out in friendship to the unknown. Powering each Voyager on its journey was not solar panels, which would be useless in the outer solar system where sunlight grows faint, but 3 radioisotope thermoelectric generators, or RTGs. These remarkable devices use the heat generated by the radioactive decay of plutonium-238 to produce electricity. At launch, each RTG generated about 157 watts, giving the spacecraft a total of 470 watts to power all its systems, about the same as several household light bulbs. The plutonium-238 has a half-life of 87.7 years, meaning that after that time, half of it would have decayed, and the RTGs would produce half as much power. The engineers designing Voyager knew this, and they planned for a mission lasting perhaps 5 years, maybe 10 if they were very lucky. The spacecraft were built to visit Jupiter and Saturn, take their measurements and pictures, and then drift into the darkness, their missions complete, their systems eventually falling silent as their power ebbed away. No one imagined that nearly 50 years later, the Voyagers would still be functioning, still transmitting, still making discoveries. But we're getting ahead of ourselves. First, there were planets to visit, moons to study, and a solar system to explore. The Planetary Encounters. The Voyager's journey through the outer solar system transformed our understanding of these distant worlds. In March 1979, Voyager 1 reached Jupiter, that massive striped globe with its great red spot, a storm larger than Earth that has raged for centuries. The spacecraft's cameras revealed details never before seen, the intricate patterns in Jupiter's clouds, the delicate structure of its faint ring system, unknown until Voyager discovered it. But perhaps more surprising were the moons. Io, the innermost of Jupiter's 4 large satellites, turned out to be the most volcanically active body in the solar system. Voyager 1's images showed volcanic plumes erupting hundreds of kilometers above Io's sulfur-covered surface, driven by tidal forces, as Jupiter's immense gravity kneaded and heated the moon's interior. It was the first time active volcanism had been observed anywhere beyond Earth. Europa, another of Jupiter's large moons, showed a surface of water ice crisscrossed with cracks and ridges, but almost no impact craters, suggesting that the ice was relatively young, constantly being renewed. Beneath that frozen shell, scientists realized, there might be an ocean of liquid water, kept warm by the same tidal heating that powers Io's volcanoes. That ocean, if it exists, could potentially harbor life, making Europa one of the most intriguing targets for future exploration. Voyager 2 arrived at Jupiter 4 months after its twin in July 1979, providing additional observations and then using Jupiter's gravity to fling itself toward Saturn. Both spacecraft reached the ringed planet, Voyager 1 in November 1980 and Voyager 2 in August 1981. Again, the discoveries came in cascades. Saturn's rings, beautiful even in telescope views from Earth, revealed themselves to be far more complex than anyone had imagined. Instead of a few broad bands, the rings consisted of thousands of individual ringlets, some braided, some with waves propagating through them, all governed by the gravitational influence of Saturn's many moons. Some small moons, called shepherd satellites, actually orbit within the rings, their gravity sculpting gaps and maintaining the edges of certain ring features. Titan, Saturn's largest moon and the second largest satellite in the solar system, proved to be a world unto itself. Voyager 1 discovered that Titan has a thick atmosphere, primarily nitrogen, making it the only moon in our solar system with a substantial atmosphere. The atmospheric pressure at Titan's surface is actually higher than Earth's, but Titan's atmosphere is opaque to visible light, hiding the surface beneath a haze of organic molecules, the kind of chemistry thought to have occurred on early Earth before life emerged. The encounter with Titan was Voyager, one's last close approach to a major body. Its trajectory, carefully calculated to provide the best views of Saturn and its moons, sent it arcing up and out of the plane of the solar system, heading toward interstellar space on a path that would never bring it close to another planet. The spacecraft's cameras would be used one more time, more than a decade later, for a special purpose, but its planetary exploration days were over. Voyager 2, however, continued onward. In January 1986, it became the first and still the only spacecraft to visit Uranus, that strange blue-green world that orbits the Sun on its side. Its axis of rotation tilted 98 degrees from the perpendicular to its orbit. Voyager 2 discovered 10 new moons orbiting Uranus and revealed its faint ring system. The planet's magnetic field proved to be tilted 60 degrees from its rotation axis and offset from the planet's center, creating a wobbling off-center magnetosphere unlike anything seen at other planets. The moons of Uranus showed remarkable diversity, despite their small sizes. Miranda, in particular, displayed a surface that looked like it had been assembled from mismatched pieces, with regions of different terrains meeting at sharp boundaries. Enormous cliffs, some 5 times the height of the walls of the Grand Canyon, scarred Miranda's surface, suggesting a violent history of tectonic activity strange for such a small, cold world. 3 years later, in August 1989, Voyager 2 completed the grand tour with a flyby of Neptune, the solar system's outermost giant planet. Neptune, even farther from the Sun than Uranus and receiving even less of its warmth, somehow proved to be a more dynamic world. Its atmosphere showed distinct cloud features including the Great Dark Spot, a storm system similar to Jupiter's Great Red Spot, and high-altitude clouds of methane ice that cast shadows on the cloud deck below. Neptune's largest moon, Triton, provided Voyager 2's last surprise in the planetary realm. Triton orbits Neptune backward, retrograde to the planet's rotation, suggesting it's a captured object, perhaps a cousin to Pluto that wandered too close to Neptune billions of years ago. Despite surface temperatures of minus 235 degrees Celsius, making it one of the coldest surfaces in the solar system, Triton proved to be geologically active. Voyager 2 observed geysers erupting on Triton's surface, nitrogen gas shooting up through the thin atmosphere, creating dark streaks on the moon's icy surface. After Neptune, Voyager 2's trajectory sent it downward relative to the plane of the solar system, heading in a different direction from Voyager 1, but toward the same ultimate destination, interstellar space. Both spacecraft had completed their primary missions with extraordinary success. They had returned thousands of images, made countless measurements, discovered new moons and rings, and fundamentally changed our understanding of the outer solar system. By any measure, they had exceeded all expectations. But in February 1990, before settling into their long cruise toward the edge of the solar system, the Voyagers had one more gift to give. At Carl Sagan's request, Voyager 1 turned its camera back toward the inner solar system and took a series of images capturing 6 planets in a family portrait. In one of those images, Earth appeared as a tiny pale blue dot, barely more than a single pixel, caught in a beam of scattered sunlight. That image, that pale blue dot suspended in a sunbeam, became one of the most iconic photographs ever taken. Sagan reflected on it in his book of the same name. "Look again at that dot," he wrote. "That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." After taking this final set of images, Voyager 1's camera was turned off forever to conserve power. There would be nothing more to photograph in the darkness ahead. The Voyagers entered what NASA designated as the Voyager Interstellar Mission. Their new goal was to reach and study the boundary between our solar system and interstellar space, to explore a region no spacecraft had ever visited, to probe the edge of the sun's influence and venture into the realm of the stars. The journey to that edge would take decades, but the Voyagers were patient. They continued onward, moving at roughly 38,000 miles per hour, carrying their golden records, their instruments still functioning, their radio signals still reaching back to Earth, growing fainter with each passing year as the distance grew, but still detectable, still interpretable, still bearing data from the frontier of human exploration, understanding the Heliosphere. To understand what the Voyagers would discover at the edge of our solar system, we first need to understand what that edge is and why it exists at all. The sun, our star, doesn't simply shine light and warmth into space. It also releases a constant stream of charged particles, a wind made of electrons and protons and other ions, that blows outward in all directions at speeds of 300 to 800 kilometers per second. This solar wind originates in the sun's outermost atmosphere, the corona, a region of plasma heated to temperatures exceeding 1 million degrees Celsius. At such temperatures, the atoms are moving so fast that not even the sun's immense gravity can hold them. They stream away into space, carrying with them magnetic field lines that are rooted in the sun and stretch outward with the expanding wind. The solar wind is tenuous, far more rarefied than the best vacuum we can create in laboratories on Earth. At Earth's distance from the sun, about 150 million kilometers, the solar wind contains only about 5 to 10 particles per cubic centimeter. For comparison, the air you're breathing right now contains roughly 2.7 times 10 to the 19th molecules per cubic centimeter. The solar wind is extraordinarily thin, yet it's real, it's measurable, and it has profound effects. One of those effects is the creation of Earth's magnetosphere, the magnetic bubble surrounding our planet that protects us from much of the solar wind's charged particle flux. When solar wind particles encounter Earth's magnetic field, they're deflected around the planet, creating a shock wave upstream of Earth and a long magnetic tail downstream. The solar wind's interaction with Earth's magnetic field also powers the auroras, those shimmering curtains of light near the poles, as particles that do penetrate the magnetic shield spiral down magnetic field lines into the upper atmosphere, exciting atoms and molecules to glow. But the solar wind doesn't just affect Earth. It fills the entire solar system, creating a bubble of solar influence called the Heliosphere. This bubble extends far beyond the orbits of the planets, billions of kilometers into space, pushed outward by the constant pressure of the solar wind. The Heliosphere is, in a real sense, the Sun's atmosphere, and everything within it, all the planets, all the asteroids and comets, all the dust and gas exists within this bubble. The Heliosphere doesn't extend infinitely, though. Far from the Sun, the solar wind encounters resistance. Between the stars, space is not truly empty. There's an interstellar medium, a thin soup of gas and dust and magnetic fields that fills the galaxy. This medium is denser than the solar wind by the time the solar wind reaches the outer solar system, and it's moving, flowing past our solar system as the Sun orbits the galactic center at a speed of about 220 kilometers per second. When the icy, supersonic solar wind encounters this interstellar medium, complex physics takes over. The solar wind slows, compresses, heats up, and creates a series of boundaries and regions that define the outer reaches of the heliosphere. Understanding these regions is key to understanding what the Voyagers discovered. The first major boundary, moving outward from the Sun, is called the termination shock. This is the point where the solar wind, which has been traveling faster than the speed of sound since it left the Sun, suddenly slows down to subsonic speeds. Shock waves form in fluids when something moves through them faster than the speed of sound in that fluid. On Earth, we're familiar with sonic booms, the shock waves created when aircraft exceed the speed of sound in air. The termination shock is similar, but it's the solar wind itself that's supersonic, and it's the pressure of the interstellar medium that forces it to slow down. At the termination shock, the solar wind's speed drops from several hundred kilometers per second to perhaps a few tens of kilometers per second. This transition is not gentle. It's a shock, a discontinuous jump in the plasma's properties. The density increases, the temperature rises, and the magnetic field becomes more turbulent. Particles can be accelerated at the shock, gaining energy from the interaction. Beyond the termination shock lies a region called the Heliosheath. This is the transition zone where the solar wind has slowed down but hasn't yet stopped entirely. In the Heliosheath, the solar wind is being deflected, turned sideways, flowing around the outside of the heliosphere toward the tail that trails behind our solar system as we move through the galaxy. The Heliosheath is thought to be a turbulent, chaotic place, with the slowed solar wind mixing and interacting with particles from the interstellar medium that have penetrated this far in. The outer boundary of the Heliosheath and of the heliosphere itself is called the Heliopause. This is where the outward pressure of the solar wind is finally balanced by the inward pressure of the interstellar medium. At the Heliopause, the solar wind essentially stops. Beyond it lies interstellar space, the realm between the stars, where the local interstellar medium dominates and the Sun's direct influence fades. There was some debate among scientists about whether there would be one more structure even farther out. By analogy with Earth's magnetosphere, which has a bow shock where the supersonic solar wind encounters Earth's magnetic field, scientists expected the heliosphere might have a bow shock where the supersonic interstellar medium encounters the heliosphere. But more recent observations suggest that the sun's motion through the local interstellar medium is subsonic, meaning the interstellar flow is moving slower than the speed of sound in that medium. If that's the case, there would be no bow shock, just a gentler bow wave, a compression of the medium ahead of the heliosphere. The overall shape of the heliosphere has been a subject of much study and debate. Early models suggested it would be roughly spherical, but we now know it's more complex. The solar wind isn't the same in all directions. It's stronger at the solar equator and weaker near the poles. The interstellar medium exerts pressure on the heliosphere, compressing it in the direction from which the interstellar wind blows and stretching it out into a long tail in the opposite direction, like a comet's tail or the magnetotail behind Earth. The Voyagers would eventually reveal that the heliosphere is also asymmetric in ways scientists hadn't fully anticipated. The two spacecraft, traveling in different directions, encountered the termination shock at different distances from the Sun, suggesting the heliosphere is not evenly shaped. These asymmetries likely result from variations in the interstellar medium and the local galactic magnetic field, factors that models are only beginning to incorporate accurately. Why does all this matter? The heliosphere serves as a shield, protecting the inner solar system from the full intensity of galactic cosmic rays. These cosmic rays are high-energy particles, mostly protons, that originate outside our solar system, accelerated to incredible speeds by supernova explosions and other violent events in the galaxy. They carry enough energy to damage living cells and electronic systems. The solar wind and the magnetic field it carries help deflect and slow these cosmic rays, reducing their intensity within the heliosphere. Earth's magnetic field provides additional protection, and our atmosphere shields us further, but the heliosphere is the first line of defense. Without it, the radiation environment in the inner solar system would be harsher, potentially affecting the evolution of life on Earth and certainly complicating any future human exploration of space. The heliosphere also protects us from some of the interstellar medium's neutral atoms. While charged particles are deflected by magnetic fields, neutral atoms can penetrate deeper. Some of these neutral atoms, particularly hydrogen, reach the inner solar system, where solar radiation can ionize them, turning them into charged particles that the solar wind then picks up. These pickup ions are eventually transported back out to the edges of the heliosphere, some of them accelerated to high energies to become what we call anomalous cosmic rays. Understanding the heliosphere, its structure, its dynamics, how it interacts with the interstellar medium, is crucial for understanding our place in the galaxy. It tells us about the environment through which our solar system is traveling, about the forces that shape the space around us, and it's this understanding that the Voyagers, designed to explore planets, would ultimately contribute to in ways their builders never imagined. As the 20th century gave way to the 21st, both Voyager spacecraft were healthy and functional, racing outward at speeds of about 3.5 astronomical units per year. Voyager 1, traveling faster and in a more direct route toward interstellar space, was in the lead, approaching the predicted location of the termination shock. Scientists waited, instruments ready for the first spacecraft ever to reach this invisible boundary at the edge of our solar system. The termination shock, first boundary. The approach to the termination shock was not marked by any visible change. No signpost floated in space to announce its presence. Instead, the Voyager's instruments watched for subtle shifts in the plasma around them, changes in particle energies and magnetic field strengths that would signal the transition from the supersonic solar wind to the subsonic Heliosheath. Starting in late 2003 and into 2004, Voyager 1 began detecting unusual particle events. Bursts of high-energy particles appeared and then subsided, suggesting the spacecraft was approaching some kind of boundary. The intensities of energetic particles, particularly protons with energies below a few million electron volts, began to increase. These particles were being accelerated somewhere ahead of the spacecraft, possibly at the termination shock itself. Then, in December 2004, Voyager 1's instruments recorded a dramatic change. The speed of the solar wind, which Voyager couldn't measure directly because its plasma instrument had failed years earlier, appeared to drop based on other indicators. The intensity of energetic ions jumped sharply. The direction of the magnetic field changed, and its strength increased. All these signs pointed to one conclusion. Voyager 1 had crossed the termination shock. The crossing occurred at a distance of 94 astronomical units from the Sun, where 1 astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers. 94 astronomical units translates to roughly 14 billion kilometers, more than 3 times the distance to Neptune, far beyond where any spacecraft had ever ventured before. Scientists analyzed the data carefully. The termination shock, they realized, was not a sharp, instantaneous transition. Voyager 1 appeared to cross back and forth through the shock region multiple times over several weeks, like dipping your toes in and out of the edge of waves at an ocean shore. This behavior suggested the shock was moving, breathing in and out, possibly in response to pressure variations in the solar wind caused by solar activity. The shock proved to be relatively weak, characterized by what's called the compression ratio, the factor by which the solar wind density increases across the shock. Voyager 1 measured a compression ratio of about 2.6, meaning the density on the downstream side was roughly 2.6 times higher than on the upstream side. This was lower than some theoretical predictions, suggesting the solar wind was transferring more of its energy to particles, particularly to pickup ions, rather than to heating the bulk plasma. One of the surprises was what didn't happen at the termination shock. Scientists had predicted that anomalous cosmic rays, those singly charged ions thought to originate from interstellar neutral atoms picked up by the solar wind, would be accelerated at the shock. They expected to see a peak in anomalous cosmic ray intensity right at the shock itself. But that peak didn't appear. The intensities of anomalous cosmic rays did increase, but they continued increasing beyond the shock as Voyager moved deeper into the Heliosheath, suggesting their source region was somewhere else, perhaps near the Heliopause itself. The magnetic field behavior also proved interesting. In the solar wind, the field had shown a regular pattern, alternating direction roughly every 13 days. This pattern arose because the Sun rotates every 26 days, and the magnetic field is rooted in the Sun. So, as the Sun turns, the field forms a spiral pattern in space, with sectors of opposite polarity alternating as the solar wind carries the field outward. This pattern has been described as resembling a ballerina's skirt, with the field lines forming a rotating pattern that sweeps past any point in space. Beyond the termination shock, this pattern changed. The time between magnetic field reversals increased dramatically, from 13 days to more than 100 days. The rotation of the Sun seemed almost irrelevant in the Heliosheath. The field was being compressed and twisted by the interaction with the interstellar medium, creating a more complex structure. Voyager 2, following its twin but taking a different path, approached the termination shock in 2007. Anticipation was high because Voyager 2 still had a functioning plasma instrument, the Plasma Science Experiment, which could directly measure the speed, density, and temperature of the solar wind. Voyager 1 had been forced to infer many properties of the shock indirectly, but Voyager 2 could measure them directly. In August 2007, at a distance of 84 astronomical units from the Sun, Voyager 2's plasma instrument detected the sudden slowdown of the solar wind. The speed dropped from roughly 400 kilometers per second to less than 100 kilometers per second. The density increased. The temperature jumped. All these changes confirmed the crossing of the termination shock, and this time there was no ambiguity. But Voyager 2's crossing location revealed something unexpected. At 84 astronomical units, Voyager 2 was 10 astronomical units closer to the Sun than Voyager 1 had been when it crossed the shock. 10 AU is about 1.5 billion kilometers, a substantial difference. Moreover, Voyager 2 was traveling in a direction roughly perpendicular to Voyager 1's path, heading toward the southern hemisphere of the Heliosphere, while Voyager 1 headed toward the northern hemisphere. This difference in crossing distances proved that the termination shock, and by extension the Heliosphere itself, is not symmetric. The Heliosphere bulges outward more in some directions than in others. The exact reasons for this asymmetry are still being studied, but they likely involve the structure of the local interstellar medium and the galactic magnetic field. The interstellar medium might be denser in some directions, pushing the termination shock closer to the Sun. Or the interstellar magnetic field might exert more pressure in certain directions. The crossings also occurred at different phases of the solar activity cycle. The Sun goes through a roughly 11-year cycle of activity, during which the number of sunspots, solar flares, and coronal mass ejections waxes and wanes. Voyager 1 crossed the termination shock during a relatively quiet phase of the solar cycle, while Voyager 2 crossed during a more active phase. The properties of the shock itself appeared different at the two locations, with Voyager 2 measuring a slightly stronger shock than Voyager 1 had encountered. Beyond the termination shock, both Voyagers found themselves in the Heliosheath, that transition zone of slowed and compressed solar wind. The plasma there proved to be hot, with temperatures reaching tens of millions of degrees Celsius, though the low density meant this heat didn't pose a threat to the spacecraft. The Heliosheath was also turbulent, with the magnetic field fluctuating rapidly in strength and direction. In the Heliosheath, both spacecraft detected a population of particles called energetic neutral atoms, or ENAs. These are neutral hydrogen atoms that have gained energy through charge exchange with hot ions in the Heliosheath. Some of these ENAs travel inward toward the Sun, where they can be detected by spacecraft like IBEX, the Interstellar Boundary Explorer, which orbits Earth and creates maps of the heliosphere by imaging these energetic neutral atoms. The journey through the Heliosheath would take years. Voyager 1, moving at about 3.6 astronomical units per year relative to the Sun, would spend nearly 8 years in this transition zone. Voyager 2, moving slightly slower, would take even longer. During this time, the spacecraft's instruments continued to monitor the plasma properties, the magnetic field, the particle populations, all providing data about this previously unexplored region. One particularly interesting observation concerned the flow of the plasma in the Heliosheath. Scientists expected the solar wind, having been slowed at the termination shock, would be deflected sideways, flowing toward the heliotail. Voyager 2 confirmed this, measuring plasma flow with a substantial sideways component. But Voyager 1, which couldn't directly measure the plasma flow, showed signatures suggesting the flow in its direction had slowed to nearly zero. This created what some scientists called the stagnation region, a zone where the solar wind plasma had slowed so much that it was barely moving. The exact nature and extent of this stagnation region remain subjects of investigation, but it suggests the Heliosheath has complex structure, with different flow patterns in different directions. All these observations, from the termination shock crossing to the properties of the Heliosheath, were valuable in themselves, revealing the high physics of how a stellar wind interacts with its surrounding medium. But they were also building toward an even more significant milestone. Somewhere ahead, at a distance scientists could only estimate, lay the Heliopause itself, the ultimate boundary of the Heliosphere, the edge where our solar system truly ends and interstellar space begins. Journey through the Heliosheath. The years Voyager 1 and Voyager 2 spent traversing the Heliosheath were years of patient measurement and careful analysis. Unlike the dramatic moments of crossing the termination shock or encountering a new planet, the journey through the Heliosheath was a slow accumulation of data points, each one adding to our understanding of this transition zone between the solar wind's domain and the realm of the stars. The Heliosheath, scientists discovered, was more dynamic than many had predicted. It wasn't simply a static region of slowed solar wind. Instead, it responded to changes in the solar wind itself, which varied with the Sun's 11-year activity cycle. When a particularly strong burst of solar wind, perhaps from a coronal mass ejection, traveled outward from the Sun, it would eventually reach the termination shock and the Heliosheath, creating pressure waves that rippled through the region. These pressure waves, sometimes called tsunamis of solar material, compressed the plasma and magnetic field as they passed. Voyager's instruments could detect these events, seeing sudden increases in plasma density and magnetic field strength followed by gradual returns to baseline levels. By tracking how long these events took to reach the spacecraft and how they evolved over time, scientists could learn about the structure and properties of the Heliosheath. The magnetic field in the Heliosheath proved to be particularly interesting. Unlike in the solar wind, where the field had that regular alternating pattern driven by the Sun's rotation, in the Heliosheath the field's behavior was more complex. The field was compressed and twisted by the interaction with the interstellar medium. Voyager 1 detected periods where the field's strength would increase and then decrease, sometimes forming what looked like magnetic bubbles, or magnetic islands, where the field lines had reconnected and pinched off. These magnetic structures, if they indeed existed, would represent regions where the solar magnetic field was being fundamentally reorganized, with field lines that had originated from opposite solar hemispheres connecting with each other. This magnetic reconnection is a process well known from studies of Earth's magnetosphere and the Sun itself, but observing it in the Heliosheath provided new insights into how magnetic fields behave in low-density plasmas. One of the key questions scientists wanted to answer was, where are the anomalous cosmic rays coming from? These particles, which had been detected near Earth for decades, were known to be interstellar neutral atoms, mostly hydrogen and helium, that had been ionized and accelerated somewhere in the outer heliosphere. The prevailing theory before Voyager was that they were accelerated at the termination shock, gaining energy as they bounced back and forth across the shock front. But, as we've seen, Voyager 1 didn't detect a peak in anomalous cosmic ray intensity at the termination shock. Instead, as both Voyagers moved deeper into the Heliosheath, the intensities of anomalous cosmic rays continued to increase. This suggested the source region might be closer to the Heliopause, or perhaps distributed throughout the Heliosheath itself. The spectra of these particles, the way their intensity varies with energy, also provided clues. At Voyager 1, the anomalous cosmic ray spectra in the Heliosheath looked almost like power laws, a characteristic shape that suggested the spacecraft was near the source region. Different models proposed different specific acceleration mechanisms, some involving magnetic reconnection in the Heliosheath, others involving acceleration at the Heliopause itself, but all agreed that the earlier, simpler picture of termination shock acceleration was incomplete. At the same time, the intensity of galactic cosmic rays, those high-energy particles from beyond our solar system, was steadily increasing. These particles, deflected and slowed by the solar wind and its magnetic field, found it easier to penetrate into the Heliosheath than into the region of supersonic solar wind beyond the termination shock. As the Voyagers moved farther from the Sun, deeper into the Heliosheath, they encountered ever higher intensities of galactic cosmic rays. This increase in galactic cosmic rays served as a kind of countdown. Scientists knew that when the spacecraft finally crossed the Heliopause, there should be a dramatic jump in galactic cosmic ray intensity. In interstellar space, with no solar wind to deflect them, these cosmic rays would reach their maximum local intensity. At the same time, particles associated with the solar wind should disappear. The transition should be clear and unmistakable, or so everyone hoped. But the Heliosheath had more surprises in store. In 2009 and 2010, Voyager 1 began detecting strange events where the intensity of particles would suddenly change, with solar particles decreasing while galactic cosmic rays increased, only to reverse again. These events, lasting days or weeks, were dubbed flux dropouts, or cosmic ray dips and peaks. They suggested Voyager 1 might be encountering some kind of structure at the edge of the Heliosheath, perhaps a region where the boundary between solar and interstellar influences was particularly complex. One possible explanation was that these events represented brief excursions beyond the Heliopause and then back, as if the boundary itself was moving back and forth past the spacecraft. If the Heliopause was not a stable, fixed boundary, but instead a dynamic one that could shift position in response to pressure variations in the solar wind or the interstellar medium, Voyager 1 might be crossing it repeatedly before making a final, permanent transition into interstellar space. Another possibility was that these events reflected some kind of pre-Heliopause structure, perhaps a magnetic layer or a region of enhanced particle acceleration just inside the final boundary. The data didn't clearly favor one interpretation over another, and scientists engaged in lively debates about what Voyager 1 was detecting. Adding to the complexity, the plasma flow measurements from Voyager 2 showed that the Heliosheath had different properties in different directions. In the direction of Voyager 2, toward the flank and southern regions of the Heliosphere, the plasma was flowing sideways, being deflected around the Heliosphere toward the tail as expected. But in Voyager 1's direction, toward the nose of the Heliosphere, the flow had slowed almost to zero in what scientists called the stagnation region. This stagnation region made sense from a theoretical perspective. If the solar wind plasma is flowing outward and then gets turned sideways to flow around the heliosphere, there has to be a region where the radial flow component drops to zero before the plasma is fully deflected. But the extent and properties of this stagnation region were not well predicted by models, and Voyager 1's observations were providing the first direct measurements of this phenomenon. Throughout these years in the Heliosheath, both spacecraft continued to function remarkably well. Their power supplies, the radioisotope thermoelectric generators, continued to decay predictably, losing about 4 watts of power per year. This steady decline meant that periodically the mission team had to make difficult decisions about which instruments or spacecraft systems to turn off to conserve power for the remaining systems. Heaters were turned off first, allowing some parts of the spacecraft to fall to temperatures far below what they were designed to tolerate, yet somehow continuing to operate. Instruments that were less critical for studying the interstellar boundary were shut down. The goal was to keep the spacecraft able to communicate with Earth and to keep operating the instruments most relevant to studying the Heliosphere's edge and interstellar space. The communication itself was a marvel. By this time, Voyager 1 was over 17 billion kilometers from Earth. Radio signals, traveling at the speed of light, took more than 16 hours to make the one-way journey. When mission controllers sent a command to the spacecraft, they had to wait more than 32 hours to know if it had been received and executed. Any problem that required troubleshooting became an exercise in extreme patience. Yet the spacecraft responded faithfully, executing commands, switching between backup systems when needed, adjusting their orientations to keep their antennae pointed at Earth despite the complex tumbling motions induced by various forces acting on them over the decades. The engineering that had gone into these machines in the 1970s, the redundancy built into their systems, the robustness of their design, all proved their worth as the Voyagers continued to function far beyond their design lifetimes. As the 2010s progressed, the data from Voyager 1 began to show more sustained changes. The intensity of galactic cosmic rays continued to climb, reaching levels higher than had ever been measured in the outer heliosphere. The intensity of solar particles continued to decline. The magnetic field strength remained elevated, and its direction seemed stable, not showing the rapid fluctuations characteristic of the Heliosheath proper. Scientists began to suspect that Voyager 1 was approaching the Heliopause, perhaps even entering a boundary layer just inside it. The spacecraft was in unknown territory, literally at the frontier of human exploration, and every day brought new data from a region no instrument had ever sampled before. The question on everyone's mind was simple. When would Voyager 1 cross into interstellar space, and how would we know when it happened? The Heliopause, edge of the solar system. The breakthrough came not from a dramatic single event, but from careful analysis of data accumulated over months. In early 2012, Voyager 1's instruments showed that the intensity of galactic cosmic rays had reached a new plateau, higher than ever before. At the same time, particles associated with the solar wind, particularly those with energies around 1 million electron volts, had dropped to very low levels. But the magnetic field direction hadn't changed significantly, which was puzzling because models predicted the interstellar magnetic field should point in a different direction from the field in the Heliosheath. Then, in late July 2012, something remarkable happened. Voyager 1's instruments detected a sharp jump in the intensity of particles in a specific energy range. Over the course of a few days, the cosmic ray count rate increased by roughly 9% and then leveled off. A month later, in late August, there was another jump, this time by about 5%, with the intensity reaching even higher levels. These increases seemed to stick. Unlike the earlier flux events that had gone up and then back down, these new high intensities persisted. At the same time, the intensity of solar energetic particles, those associated with the Sun's activity, dropped to nearly zero. The spacecraft appeared to be measuring particles from two distinct populations: galactic cosmic rays from interstellar space, which had reached their maximum local intensity, and the remnants of solar particles, which had essentially disappeared. Scientists analyzing the data realized what had happened. On August 25, 2012, Voyager 1 had crossed the Heliopause. The spacecraft had left the Heliosphere and entered interstellar space. After 35 years of travel, after covering more than 18 billion kilometers, Voyager 1 had become the first human-made object to leave our solar system's protective bubble and venture into the space between the stars. The announcement, made by NASA in September 2013 after nearly a year of careful analysis and debate, was momentous. Humanity had reached interstellar space. We had extended our presence beyond the realm of the Sun's direct influence, into a region shaped by the galaxy itself. But the announcement also came with caveats and questions. The magnetic field direction hadn't changed at the Heliopause, at least not in the way many scientists had expected. The field just inside the Heliopause was oriented at about a 40-degree angle to the field expected in the local interstellar medium. Across the boundary, the field's direction remained the same, only its strength and steadiness changed. This observation challenged some theoretical models. Why would the magnetic field not rotate to align with the interstellar field at the Heliopause? Some scientists suggested that the interstellar field itself might be oriented differently than the models assumed. Others proposed that the Heliopause region had more complex structure, perhaps with layers where the magnetic field gradually rotated. Still others argued that magnetic reconnection at the Heliopause might allow field lines from the Heliosphere and from the interstellar medium to connect, creating a region where the field's direction was a mix of both influences. Despite these puzzles, the particle data was compelling. Voyager 1 was measuring a plasma density roughly 40 times higher than in the Heliosheath, consistent with the denser interstellar medium. The spectrum of cosmic rays, the way their intensity varied with energy, matched what would be expected in interstellar space. Multiple lines of evidence pointed to the same conclusion. There was one major gap in the data, though. Voyager 1's plasma science experiment, the instrument that could directly measure the plasma properties, had failed back in 1980. Without it, scientists couldn't directly measure the density, temperature, or flow speed of the plasma around the spacecraft. They had to infer these properties from indirect measurements, particularly from plasma oscillations. Plasma oscillations occur when electrons in the plasma are disturbed, and then oscillate at a frequency that depends on the plasma's electron density. Think of it like ringing a bell. The frequency of the sound depends on the bell's properties. When events like solar eruptions sent shocks through the plasma, they would trigger these oscillations, which Voyager 1's plasma wave system could detect. By measuring the oscillation frequency, scientists could calculate the plasma density. The problem was that these oscillation events were rare. Voyager 1 had detected them only a handful of times, once in 2012, again in 2013, and again in 2014. Each time when a particularly strong disturbance from the Sun reached the spacecraft's location. Between these events, there was no way to measure the plasma density directly. This is where Voyager 2's continuing journey became crucial. Voyager 2, following its twin but traveling slower and in a different direction, was still in the Heliosheath, but it was approaching the Heliopause. And, unlike Voyager 1, Voyager 2 still had a working plasma science experiment. When Voyager 2 crossed the Heliopause, it would be able to directly measure the transition, providing data that could confirm and complement Voyager 1's observations. That crossing came on November 5, 2018. Voyager 2 was at a distance of about 119 astronomical units from the Sun, about 18 billion kilometers, similar to Voyager 1's crossing distance but in a different direction, toward the southern and trailing edge of the Heliosphere, rather than the northern and leading edge. The plasma science experiment on Voyager 2 detected a sudden, steep decline in the speed of the solar wind, plasma. The speed dropped from about several tens of kilometers per second to essentially zero. The density of the plasma jumped dramatically, increasing by a factor of 20 or more. These measurements unambiguously confirmed the crossing of the Heliopause. At the same time, Voyager 2's particle instruments detected the expected changes. The intensity of galactic cosmic rays jumped up, while solar particles vanished. The magnetic field strength increased and became steadier. All the signatures of entering interstellar space were present, and this time there could be no debate because the plasma measurements were direct and clear. Interestingly, Voyager 2 also found that the magnetic field direction didn't change significantly at the Heliopause, just as Voyager 1 had observed. With measurements from two locations, scientists could now be more confident that this was a real feature of the boundary, not just a local anomaly. The magnetic field in the interstellar medium just beyond the Heliopause appeared to be running nearly parallel to the field in the Heliosheath, at least at the locations where the Voyagers crossed. One explanation that gained traction was that the large-scale interstellar magnetic field is oriented differently than the small-scale local field right at the Heliopause. The Voyagers, having just crossed the boundary, were still very close to it, still in what some scientists call the very local interstellar medium that might be influenced by the heliosphere's presence. The magnetic field might rotate to align with the larger-scale galactic field at some distance beyond the Heliopause. Another important observation from Voyager 2 was evidence of particle leakage across the Heliopause. Some solar particles appeared to be escaping from the heliosphere into interstellar space, while some interstellar particles were penetrating into the Heliosheath. The Heliopause wasn't a perfect barrier. It was more like a membrane, mostly keeping the two regions separate but allowing some mixing, some exchange of particles. This leakage might occur through several mechanisms. Magnetic reconnection at the Heliopause could open up channels through which particles could flow. The Heliopause itself might not be perfectly smooth, but could have ripples or waves that allow particles to cross more easily in some places. Or the Heliopause might be porous in a more general sense, with the plasma physics allowing a steady trickle of particles in both directions. Voyager 2's crossing location also confirmed that the Heliopause is not perfectly spherical. At 119 astronomical units, Voyager 2 was about 2 astronomical units closer to the Sun when it crossed than Voyager 1 had been. Given the different directions and the different phases of the solar cycle when the crossings occurred, this small difference wasn't necessarily surprising, but it added to the evidence that the heliosphere's shape is complex and variable. Remarkably, despite crossing at different times in The solar cycle, when the sun's activity and therefore the solar wind's pressure were quite different. Both Voyagers crossed the Heliopause at nearly the same distance from the sun. Scientists had expected the Heliopause to move in and out with the solar cycle, expanding when the solar wind was strong and contracting when it was weak. But the similarity in crossing distances suggested that something was stabilizing the Heliopause, preventing it from moving as much as expected. The answer appeared to lie in the strength of the interstellar magnetic field. Both Voyagers measured a field strength in the very local interstellar medium of about 5 to 6 microgauss, roughly twice what had been predicted before Voyager. This stronger magnetic field exerts more pressure on the Heliopause, acting like a straitjacket that suppresses most of the expansion and contraction that would otherwise occur with the solar cycle. With both Voyagers now in interstellar space, scientists had an unprecedented opportunity. For the first time, we had working instruments in the space between the stars, measuring conditions directly rather than trying to infer them from remote observations. The Voyagers were sampling the local interstellar medium, the material that fills the space around our solar system, and sending back data about its properties. What does it mean to say Voyager has left the solar system? This is a question that deserves careful consideration. The sun's gravitational influence extends much farther than the Heliopause. Thousands of astronomical units away, perhaps as far as 1 or 2 light years, lies the Oort cloud, a spherical shell of icy objects orbiting the sun. These objects are gravitationally bound to the sun, part of our solar system in that sense. The Voyagers won't reach the inner edge of the Oort cloud for another 300 years, and they won't clear the outer edge for perhaps 30,000 years. So, in a gravitational sense, the Voyagers are still in the solar system and will be for millennia. But in terms of the sun's direct influence through the solar wind, in terms of the plasma environment, the Voyagers have left the region dominated by our star and entered the region dominated by the galaxy. They have crossed from the solar neighborhood into the interstellar neighborhood. This distinction matters because it defines what the Voyagers are now studying. They're no longer measuring the solar wind or the heliosphere's structure. They're measuring interstellar space itself, the medium between the stars, helping us understand the conditions our solar system is traveling through as the sun orbits the galactic center. This information feeds into models of how the heliosphere forms and evolves, how it protects the planets from galactic radiation, and how it might change as we move through different regions of the galaxy over millions of years. The crossings of the Heliopause by Voyagers. 1 and 2 represented a historic achievement, one that will be remembered as long as human civilization endures. For the first time, we had extended our reach beyond the sun's domain. We had touched the stars, or at least the space between them, and the Voyagers were still sending data, still functioning, still making discoveries in this new realm. What would they find in interstellar space? What secrets would the space between the stars reveal? The Wall of Fire discovery. Among the many discoveries the Voyagers made as they approached and crossed the Heliopause, one of the most dramatic was the detection of extreme temperatures at the boundary of our solar system. Scientists analyzing the data found that near the Heliopause, the plasma reaches temperatures between 30,000 and 50,000 Kelvin, which translates to roughly 54,000 to 90,000 degrees Fahrenheit. To put this in perspective, the surface of the sun is about 5,800 Kelvin, so the temperatures at the Heliopause are multiple times hotter than the solar surface. This discovery led to headlines about a wall of fire at the edge of the solar system, a phrase that captured public imagination even as it required careful scientific context. How could there be temperatures hotter than the Sun's surface at the edge of the solar system, in a region billions of kilometers from the Sun? And if these temperatures are so extreme, why didn't the Voyager spacecraft melt or burn up? The answers lie in understanding what temperature means in the rarefied conditions of space. Temperature is a measure of the average kinetic energy of particles in a substance, how fast the particles are moving. In the dense atmosphere of Earth, where particles constantly collide with each other and with any object in the environment, high temperature means rapid transfer of thermal energy. Touch a hot stove, and the fast-moving atoms in the metal rapidly transfer energy to your skin through countless collisions, causing a burn. But at the Heliopause, the particle density is extraordinarily low. We're talking about perhaps 1/10 of a particle per cubic centimeter in the outer Heliosheath, and perhaps 1 particle per cubic centimeter in the nearby interstellar medium. These are densities far lower than the best vacuum we can create in laboratories on Earth. Even though individual particles might be moving at speeds corresponding to tens of thousands of degrees, there are so few particles that they rarely collide with anything. A spacecraft passing through this region experiences very few particle impacts. The spacecraft's surfaces might be struck by a few particles per second, and while each particle carries significant energy, the total energy transfer is minimal because there are so few of them. It's similar to the difference between being in a room with air at room temperature and being in the same room if you removed all but a tiny fraction of the air molecules but heated the remaining ones to thousands of degrees. You wouldn't feel much heat because there would be so few molecules to transfer energy to you. So the Voyager spacecraft, while passing through plasma with temperatures of tens of thousands of Kelvin, didn't heat up significantly. The low particle density meant the actual heat transfer was negligible. The spacecraft's internal temperature remained relatively stable, governed more by the decay heat from their radioactive power sources and the radiation of heat into space than by the surrounding plasma temperature. But why is the plasma so hot at the Heliopause? The answer involves the physics of shock waves and compression. When the solar wind particles reach the termination shock and are suddenly slowed down, much of their kinetic energy, their energy of motion, is converted into thermal energy, random motion of the particles in all directions. This heats the plasma in the Heliosheath. Additionally, at the Heliopause itself, particles from the solar wind and from the interstellar medium are compressed together. The compression increases the plasma density, and it can also increase the temperature. The exact details depend on complex plasma physics, including the role of magnetic fields, particle acceleration mechanisms, and energy transfer processes. Near the Heliopause, there are also regions where charged particles become trapped and compressed between the inflowing interstellar medium and the outflowing solar wind. These trapped particles can be accelerated to high energies through various mechanisms, creating zones of particularly hot plasma. The result is a patchwork environment, with some regions hotter than others, creating what's been colorfully described as a wall of fire, but is more accurately a boundary layer of high-temperature, low-density plasma. The magnetic field plays a crucial role in shaping this boundary. The Voyagers detected that the magnetic field strength increases as you approach the Heliopause from the inside. The field lines, carried outward by the solar wind, are compressed at the Heliopause as the solar wind slows and piles up. This compressed magnetic field can trap particles, bouncing them back and forth, accelerating them to high energies in the process. At the same time, the interstellar magnetic field presses inward against the heliosphere. The tension between these two magnetic fields, one rooted in the sun and carried out by the solar wind, the other part of the local interstellar medium and shaped by galactic processes, creates a dynamic, turbulent boundary. The fields don't smoothly merge. Instead, they press against each other, and in places they may reconnect, with field lines breaking and rejoining in new configurations. This magnetic reconnection can be particularly effective at accelerating particles. When field lines reconnect, they release magnetic energy that goes into accelerating nearby charged particles. These particles, now moving at high speeds, contribute to the high temperatures measured at the boundary. Some of these particles may also be the source of the anomalous cosmic rays that Voyager detected throughout the Heliosheath and near the Heliopause. The wall of fire description, while dramatic, also captures something genuine about the nature of the Heliopause. This isn't a calm, quiet boundary. It's an active, energetic region where two very different plasmas meet and interact. The solar wind, which has traveled billions of kilometers from the Sun, finally meets its match in the interstellar medium. The collision creates turbulence, heating, particle acceleration, and magnetic field restructuring. Interestingly, the temperatures measured near the Heliopause vary depending on location. Voyager 1 and Voyager 2, crossing at different places and different times, measured somewhat different conditions. This suggests the Heliopause is not uniform, but has structure and variability. Some of this variation might be driven by the solar cycle, with the properties of the solar wind changing as the Sun's activity waxes and wanes. Some might be driven by variations in the local interstellar medium itself, which is not perfectly uniform but has its own structure and dynamics. The discovery of these extreme temperatures added another layer to our understanding of the heliosphere's boundary. It showed that the heliopause is not just a passive boundary where two plasmas meet. It's an active region where energy is being deposited, particles are being accelerated, and complex processes are occurring. Understanding these processes helps us understand not just our own heliosphere, but also the interactions between stars and the interstellar medium throughout the galaxy. Many stars have stellar winds, outflows of plasma driven by the star's energy. When these winds interact with the surrounding interstellar medium, they create structures analogous to our heliosphere. By studying our heliosphere in detail, including the high temperatures and particle acceleration at the heliopause, we gain insights into these other stellar wind bubbles, most of which are too far away to study directly with current technology. The Voyager's measurements of the heliopause temperatures also have implications for understanding cosmic ray modulation. Cosmic rays, those high-energy particles from beyond our solar system, must cross the heliopause to reach the inner solar system. If the heliopause is a region of turbulent magnetic fields and hot plasma, it could affect how cosmic rays are scattered and transported. Understanding this helps us predict how cosmic ray intensities might change over time, which is important for planning future deep space missions and for understanding the radiation environment that early Earth experienced before life emerged. Despite the dramatic nature of these temperatures, it's important to remember that the heliopause, this wall of fire, is not a barrier in any physical sense. Objects can pass through it, as the Voyagers demonstrated. Interstellar neutral atoms, which aren't affected by magnetic fields because they carry no charge, pass through the heliopause readily. Some neutral atoms from the interstellar medium actually penetrate all the way to the inner solar system, where they can be detected by spacecraft near Earth. These neutral atoms, when they enter the heliosphere and become ionized by solar radiation or by collision with solar wind particles, become pickup ions. They're picked up by the solar wind's magnetic field and carried along, eventually making their way back out to the outer heliosphere, where some of them might be accelerated to become anomalous cosmic rays. The cycle of neutral atoms coming in, being ionized, being carried out, and possibly being accelerated creates a dynamic connection between the interstellar medium and the heliosphere. The wall of fire at the Heliopause, then, is both a boundary and a region of mixing. It separates two distinct plasma regimes, but it also allows for exchange and interaction. It's a place where the sun's influence ends but doesn't vanish abruptly, where the galaxy's influence begins but is modified by the sun's proximity. It's a transition zone, complex and variable, where some of the most interesting physics in the solar system occurs. As Voyager 1 and Voyager 2 crossed this region and moved into the interstellar medium beyond, they continued to measure its properties. The temperatures gradually decreased as they moved away from the boundary. The magnetic field strength remained relatively high but stopped increasing. The plasma density settled into values characteristic of the local interstellar medium. The spacecraft had transitioned from one regime to another, from the realm of the sun to the realm of the stars, carrying with them their instruments still faithfully recording and transmitting data about this new environment. The Interstellar Hum. After Voyager 1 entered interstellar space in 2012, its plasma wave system continued to operate, listening to the electromagnetic environment around the spacecraft. For years, the instrument detected occasional bursts of plasma oscillations, triggered by shock waves from solar eruptions that traveled outward through the heliosphere and into interstellar space. These events, while interesting, were intermittent, leaving long gaps during which the plasma wave instrument detected nothing unusual. Then, starting in 2017, scientists analyzing the Voyager 1 data began to notice something different. Between the dramatic bursts from solar events, there was a faint, persistent signal. It was very weak and it was narrow in bandwidth, meaning it appeared at a specific frequency range rather than being spread across many frequencies. This signal hadn't been noticed earlier because it was so faint that it only became apparent when researchers averaged many months of data together, smoothing out random noise to reveal the underlying pattern. The frequency of this signal was around 3 kilohertz, about 3,000 cycles per second. This was significantly higher than the frequency of plasma oscillations detected in the Heliosheath, which had been around a few hundred hertz. The frequency difference made sense because plasma oscillation frequency depends on the square root of the electron density. The higher frequency in interstellar space indicated a higher electron density, consistent with Voyager 1 having moved from the Heliosheath, where the density was low, to the interstellar medium, where it was higher. But what was causing this persistent oscillation? Unlike the dramatic bursts triggered by solar events, this signal was steady, always present, like a hum or a drone. The researchers, led by Stella Koch-Ocker, a graduate student at Cornell University, proposed that they were detecting quasi-thermal noise or thermally excited plasma oscillations. Essentially, the random thermal motion of electrons in the plasma was creating weak fluctuations in the local electric field, and these fluctuations had a characteristic frequency related to the plasma density. Think of it as the plasma's natural vibration frequency, like the resonance of a tuning fork. The electrons in the plasma jitter back and forth due to their thermal energy, and this jittering creates oscillations at the plasma frequency. These oscillations are extremely weak, much weaker than the oscillations triggered by shock waves or other dramatic events. But with sensitive enough instruments and enough signal averaging, they can be detected. The discovery of this interstellar hum was significant for several reasons. First, it provided a way to measure the plasma density continuously, without waiting for rare solar events to trigger strong plasma oscillations. By monitoring the frequency of the hum, scientists could track how the plasma density changed as Voyager 1 moved through interstellar space. This would reveal information about the structure of the local interstellar medium on small scales. Indeed, the data showed that the plasma density wasn't perfectly uniform. There were fluctuations, variations in density on scales of a few astronomical units. These fluctuations likely reflect turbulence in the interstellar medium, eddies and swirls in the plasma as it flows through the galaxy. Understanding this turbulence is important for understanding how the interstellar medium behaves, how it transports energy and particles, and how it interacts with structures like stellar wind bubbles. Second, the persistent nature of the hum suggested that there's more low-level activity in the interstellar medium than scientists had previously thought. Before Voyager, our knowledge of the interstellar medium came primarily from remote observations, looking at how starlight is absorbed or scattered by interstellar gas and dust, or measuring radio emissions from ionized regions. These observations provided information about the large-scale properties of the medium, but couldn't detect subtle, small-scale plasma oscillations. Voyager's detection of the hum showed that the interstellar medium is not a completely quiescent, quiet place between dramatic events. There's a background level of plasma activity, driven by the thermal motion of particles, that pervades the medium. This activity might play a role in dissipating turbulent energy, in scattering cosmic rays, or in other processes that shape the interstellar environment. James Cordes, a senior author on the study, compared the interstellar medium to gentle rain. Most of the time, it's this quiet, persistent background. But occasionally, when a solar eruption sends a shock wave through, it's like lightning in a thunderstorm. A dramatic event that briefly dominates the signal before things return to the gentle rain. Both the background and the storms are important for understanding the complete picture. Third, the ability to measure the plasma density continuously along Voyager 1's path allowed scientists to create a density profile, showing how the density varied with distance from the Heliopause. This profile revealed an interesting feature. The density wasn't constant. Instead, there appeared to be a gradual increase in density as Voyager 1 moved farther from the Heliopause, suggesting there might be a density gradient in this region of interstellar space. One possible explanation for this gradient involves the interaction between the Heliosphere and the interstellar medium. The Heliosphere, as it plows through the interstellar medium, creates a bow wave or compression ahead of it, similar to how a boat creates a bow wave as it moves through water. This compression would increase the density of the interstellar medium in the region just ahead of the Heliosphere. Voyager 1, having crossed the Heliopause, would be moving through this compressed region, and as it traveled farther, it might be moving deeper into the compressed zone, encountering gradually higher densities. Another possibility is that the local interstellar medium itself has structure, with the density varying naturally in this region of space. The Sun is currently passing through what's called the local interstellar cloud, a region of somewhat higher density within the larger local bubble, a cavity in the interstellar medium created by ancient supernova explosions. The structure of the local cloud, how its density varies spatially, is not well known, and Voyager's measurements are providing the first direct sampling of it. The Interstellar Hum also provided a way to check and refine the measurements of plasma density, derived from the occasional strong oscillation events. When a solar shock passed Voyager 1, it would trigger a strong plasma oscillation that was easily detected, and the frequency of that oscillation would yield a density measurement. But these events were rare, happening only every year or two. Between these events, the hum provided density information, allowing scientists to connect the dots and see how the density evolved over time. This continuous monitoring capability is particularly valuable given that Voyager 1's plasma science experiment, the instrument that could directly measure plasma properties, failed decades ago. Without the plasma instrument, the mission relies on indirect methods to infer plasma density and the plasma wave measurements. Both the strong oscillations from shocks and the weak persistent hum are crucial for providing this information. As of the latest data, Voyager 1 has now traveled more than 10 astronomical units beyond the Heliopause, and the hum continues. The spacecraft is providing a running record of the plasma density in the very local interstellar medium, a record that spans multiple AU and multiple years. This is data that could not be obtained any other way, not from Earth-based observations, not from telescopes in space, but only from a spacecraft actually present in interstellar space, measuring the plasma in situ. The discovery of the interstellar hum also suggests that Voyager 1 will be able to continue providing useful plasma density measurements for as long as the plasma wave system remains operational. This could extend years into the future, gradually building up a longer baseline of measurements, allowing scientists to study larger-scale structures in the interstellar medium and to track how the medium changes over time. Interestingly, Voyager 2, which crossed the Heliopause 6 years after Voyager 1, should also be detecting this hum, though at a slightly different frequency due to differences in plasma density at its location. Comparing the hum detected by the two spacecraft, which are moving through different regions of the local interstellar medium, could reveal how the medium varies from place to place. The gentle hum of interstellar plasma detected by an instrument on a spacecraft launched in 1977 using technology from that era represents a remarkable achievement. It shows that careful engineering and patient analysis can extract profound insights from data, that even faint signals can be meaningful, and that the universe is full of phenomena waiting to be discovered if we only listen carefully enough. As the Voyagers continue their journey, moving ever deeper into the space between the stars, this hum will likely continue. A quiet reminder that even in the vast emptiness of interstellar space, there is structure, there is activity, and there are still secrets waiting to be revealed. Our interstellar space revelations. With both Voyager spacecraft now in interstellar space, scientists had an unprecedented opportunity to study this realm directly. What they found was a region both familiar and strange, a place where the influences of our sun fade but do not disappear entirely, and where the galaxy's presence becomes unmistakable. The interstellar medium immediately beyond the Heliopause is sometimes called the very local interstellar medium, or VLISN, to distinguish it from the broader interstellar medium farther away. This very local region is still influenced by the proximity of the Heliosphere. The Sun's presence creates a cavity in the interstellar medium, compressing it at the edges, potentially modifying its magnetic field and certainly affecting how cosmic rays and other particles move through it. One of the first things the Voyagers confirmed about the VLISM was its density. Both spacecraft measured plasma densities around 0.1 particles per cubic centimeter in this region, significantly higher than the densities in the Heliosheath, which were around 0.002 to 0.005 particles per cubic centimeter. This factor of 20 to 40 increase in density across the Heliopause matched theoretical expectations, confirming that the interstellar medium is indeed denser than the solar wind. The composition of the plasma in the VLISM also differs from the Heliosheath. The Heliosheath contains primarily particles of solar origin, electrons and protons from the solar wind, along with some pickup ions and particles that have diffused in from interstellar space. The VLISM, in contrast, contains primarily interstellar plasma, material that has never been part of the solar wind. This plasma is older, having been processed through cycles of star formation and stellar evolution over billions of years. The temperature of the VLISM proved to be quite warm, tens of thousands of Kelvin, which was expected based on observations of the local interstellar cloud from Earth. This warmth comes from a combination of factors. The galaxy is full of energetic events like supernova explosions that heat the interstellar medium. Cosmic rays passing through the medium deposit energy. Turbulence and shocks also heat the gas. The result is that the interstellar medium in our region of the galaxy is not cold but relatively warm, at least in terms of particle energies. One of the most surprising findings from both Voyagers was the behavior of the magnetic field in the VLISM. As mentioned earlier, the field didn't rotate at the heliopause in the way many scientists had expected. The magnetic field in the Heliosheath and the field in the VLISM, just beyond the heliopause, were nearly parallel, aligned to within about 40 degrees or so. This observation has important implications for understanding the heliopause's structure. If the fields are nearly parallel, it suggests that magnetic reconnection might occur at the boundary, with field lines from the heliosphere connecting with field lines in the interstellar medium. This reconnection would allow particles and energy to be exchanged across the boundary more easily than if the fields were perpendicular. Alternatively, the near-parallel alignment might indicate that the large-scale interstellar magnetic field in our region of space happens to be oriented similarly to the field in the outer heliosphere. The galactic magnetic field, after all, has a particular direction set by the structure and dynamics of our Milky Way galaxy. If the solar wind carries out a field that, by chance, is roughly aligned with the galactic field, the result would be the near-parallel configuration the Voyagers observed. With measurements from both Voyagers, scientists could estimate the strength and direction of the interstellar magnetic field more precisely. The field's strength appears to be around 5 to 7 microgauss, which is actually stronger than the field in the Heliosheath, but weaker than the field near the heliopause itself. The direction of the field, based on combining data from both spacecraft, seems to be roughly perpendicular to the plane of the galaxy, though uncertainties remain. Understanding the local interstellar magnetic field is important for several reasons. This field affects how cosmic rays propagate through the region. It influences the shape and structure of the heliosphere, and it's part of the larger galactic magnetic field, which plays a role in star formation, in shaping the structure of the galaxy, and in accelerating the highest energy cosmic rays we detect. Another revelation from the Voyagers in interstellar space concerns the permeability of the Heliopause. Both spacecraft detected evidence that the boundary is not perfectly sealed. Voyager 2, in particular, with its working plasma instrument, observed particles that appeared to be leaking from the Heliosheath into the VLISM. Similarly, some interstellar particles seem to be penetrating back into the Heliosheath. This leakage might occur through several mechanisms. Magnetic reconnection, if it's happening at the Heliopause, would create temporary channels through which particles could flow. The Heliopause itself might be rippling or waving, creating times and places where the boundary is more permeable. Or the Heliopause could have a more porous structure on microscopic scales, allowing particles to diffuse across. The dynamic nature of the Heliopause became increasingly apparent from the Voyager's data. The boundary is not static, but responds to pressure changes in the solar wind and possibly to variations in the interstellar medium as well. When a particularly strong burst of solar wind reaches the Heliopause, it can push the boundary outward, temporarily expanding the Heliosphere. When the pressure subsides, the boundary moves back inward. This breathing of the Heliosphere, expanding and contracting with the 11-year solar cycle and with shorter-term solar activity, means the Heliopause's location is always changing. The Voyagers crossed at particular moments, at particular locations, and at different times the boundary might have been kilometers or tens of kilometers away from where the spacecraft measured it. This variability is one reason why the two spacecraft, even though they crossed in different directions, crossed at similar distances from the Sun, both around 120 astronomical units. The Heliopause, on average, is at a certain distance, but that distance fluctuates. Observations from the IBEX mission, which orbits Earth and images the Heliopause by detecting energetic neutral atoms emitted from the boundary region, have shown that the Heliopause has structure. There are regions where it's brighter in ENAs, and regions where it's dimmer, suggesting variations in the processes occurring at the boundary. Some of these variations might be long-lived, reflecting the heliosphere's asymmetric shape. Others might be transient, reflecting the Heliopause's dynamic response to solar and interstellar conditions. As the Voyagers continue to move through the VLISM, they're gradually sampling a larger volume of this region. Each year, they travel about 3 to 3.6 astronomical units, adding to the spatial baseline of their measurements. Over time, this will reveal whether the properties of the VLISM are uniform, or whether there are gradients, structures, or boundaries within it. One question scientists are particularly interested in is whether there's a transition from the very local interstellar medium, which might be disturbed by the heliosphere's presence, to the undisturbed local interstellar medium farther away. If such a transition exists, the Voyagers might eventually detect it, perhaps seeing changes in plasma density, magnetic field strength, or cosmic ray intensity as they move beyond the heliosphere's sphere of influence. The cosmic ray intensities measured by the Voyagers in the VLISM are the highest they've ever recorded. These intensities represent the local galactic cosmic ray background, the radiation environment that pervades our region of the galaxy. Understanding this background is important for assessing the radiation hazards for future interstellar missions and for understanding the radiation history of our solar system. Interestingly, even in the VLISM, cosmic ray intensities show some variation. There appear to be small-scale fluctuations, possibly related to the turbulent structure of the magnetic field, that cause the cosmic ray intensity to rise and fall slightly as the Voyagers move through different regions. These fluctuations provide information about how cosmic rays are scattered and transported by the turbulent magnetic field, a process that's important for understanding cosmic ray propagation throughout the galaxy. The Voyager's journey through interstellar space has also provided insights into the overall structure of the Heliosphere. By combining data from both spacecraft with observations from IBEX and other missions, scientists have refined models of the heliosphere's shape. It's not spherical, but more complex, with the heliopause closer to the Sun in some directions than in others, reflecting the asymmetric pressure from the interstellar medium and the structure of the local interstellar magnetic field. These models suggest the heliosphere has a long tail, the heliotail, stretching out behind the solar system as we move through the galaxy. This tail might extend hundreds or even thousands of astronomical units, creating a wake in the interstellar medium. Neither Voyager is traveling in the direction of the tail, so they can't sample it directly, but their measurements of the nose and flank regions of the heliosphere provide crucial data for constraining the models. All these revelations from the VLISM are fundamentally changing how we understand our place in the galaxy. We're not isolated. The solar system is embedded in a complex, dynamic interstellar environment. The Sun's influence creates a bubble, the heliosphere, but that bubble is relatively small on galactic scales and is constantly interacting with the surrounding medium. What happens outside the heliosphere affects what happens inside it, and vice versa. The dying light, power, and longevity. As remarkable as the Voyager's discoveries have been, the spacecraft face an inevitable limitation. They are slowly running out of power. The radioisotope thermoelectric generators that have powered them for nearly 5 decades are gradually decaying, and with each passing year, there is less energy available to run the spacecraft's systems. The RTGs work by converting heat from radioactive decay into electricity through thermocouples, devices that generate a voltage when there's a temperature difference across them. Inside each RTG are pellets of plutonium-238 dioxide. As the plutonium-238 atoms undergo radioactive decay, they emit alpha particles, helium nuclei, which strike the surrounding material and convert their kinetic energy into heat. This heat is conducted to one side of the thermocouples, while the other side is kept cool by radiating heat into space. The temperature difference generates electrical current. Plutonium-238 has a half-life of 87.7 years, meaning that after that time, half of the original plutonium will have decayed into uranium-234 and other products. Since the Voyagers were launched in 1977, they've been operating for about 48 years as of early 2026. That means roughly half a half-life has passed, and the plutonium is producing approximately 70 to 75% of the heat it originally produced. However, the power output of the RTGs has declined even faster than the radioactive decay would suggest. This is because the thermocouples themselves degrade over time. The materials in the thermocouples gradually change their properties due to radiation damage, thermal stress, and other factors. As a result, they become less efficient at converting heat into electricity. The combination of decreasing heat production and decreasing conversion efficiency means the RTG, so power output drops by about 4 watts per year. At launch, the 3 RTGs on each Voyager produced a total of about 470 watts. As of 2026, each spacecraft is generating approximately 225 watts, less than half the original power. This is still enough to run some of the spacecraft systems, but it's far from enough to run everything. Difficult decisions have had to be made about what to turn off. Over the years, the mission team has systematically shut down systems to conserve power. First to go were the instruments no longer needed after the planetary flybys. The imaging cameras on both spacecraft were turned off in 1990 after the famous pale blue dot photograph. The infrared and ultraviolet spectrometers were shut down. The photopolarimeter went dark. Heaters were another major power draw. The spacecraft were designed to operate in the relatively warm environment near the planets, where temperatures, while cold by Earth standards, were not as extreme as in interstellar space. To keep the electronics and other components from freezing, the spacecraft were equipped with heaters. But as power became scarce, these heaters were turned off one by one. Remarkably, many systems continued to function even at temperatures far below their design specifications. The ultraviolet spectrometer on Voyager 1, for example, was designed to operate down to minus 35 degrees Celsius. When its heater was turned off in 2011, the instrument's temperature dropped to minus 79 degrees Celsius. It kept working. This resilience, far beyond what the engineers who built it in the 1970s expected, speaks to the robust design of the spacecraft. But there are limits to this resilience. Eventually, components do fail when pushed too far beyond their operating ranges. And, more critically, the spacecraft need to keep their fuel lines from freezing. The Voyagers use small thrusters to maintain their orientation, keeping their antennae pointed at Earth. These thrusters are fed by hydrazine fuel lines. If those lines freeze, the thrusters stop working. The spacecraft can no longer orient itself, and communications with Earth are lost. To prevent this, the mission team has had to be very strategic about which heaters to keep running. Some heaters are essential and must stay on. Others can be turned off, allowing the power to be redirected to science instruments. This balancing act has been going on for years, with engineers constantly recalculating power budgets and making trade-offs. In recent years, as the power situation became more critical, the team implemented an innovative solution. Each spacecraft has a voltage regulator that keeps the electrical system running at a stable voltage. If the voltage fluctuates too much, it could damage the instruments. To protect against this, the spacecraft have a backup circuit that can draw on a small reserve of power from the RTGs. This reserve power was meant to be saved for emergencies. But the engineers realized they could use this reserve power to keep the instruments running a bit longer. By accepting a slight increase in voltage variability and monitoring the system carefully, they could tap into the reserve and gain a few more years of operation. This change was implemented on Voyager 2 in 2023 and has successfully extended the spacecraft's scientific life. Even with these measures, the clock is ticking. In February 2025, the mission team turned off Voyager 1's cosmic ray subsystem, and in March 2025, they shut down Voyager 2's low-energy charged particle instrument. Each spacecraft now operates 3 science instruments. The plan is to shut down Voyager 2's cosmic ray subsystem in 2026. With this strategy, mission engineers believe the 2 probes could have enough electricity to continue operating with at least 1 science instrument into the early 2030s. But they are also mindful that the Voyagers have been weathering deep space for 48 years, and that unforeseen challenges could shorten that timeline. In late 2023, Voyager 1 suffered a serious malfunction when a computer chip in its flight data subsystem failed. For months, the spacecraft transmitted only garbled data. It took the engineering team, working with the 45-hour round-trip communication delay, until mid-2024 to identify the problem and implement a workaround by rearranging code away from the corrupted memory. The fact that they succeeded, despite the spacecraft being 15 billion miles away and using hardware and software from the 1970s, is itself a testament to human ingenuity. The exact timeline for when the Voyagers will fall silent depends on several factors. If the RTGs continue to degrade at the current rate, and if no major system failures occur, the spacecraft might last into the mid-2030s. If the degradation accelerates, or if a critical system fails, the end could come sooner. The mission team is doing everything possible to extend operations, but ultimately, physics and engineering impose limits that no amount of cleverness can overcome. What will happen when the Voyagers finally fall silent? The spacecraft will continue on their trajectories, moving at about 38,000 miles per hour relative to the Sun. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445, a red dwarf in the constellation Camelopardalis. It won't be a close encounter in any practical sense. The spacecraft will be too small and dark to be visible to any observers around that star, and it will pass through the outer reaches of that star's Oort cloud analog without incident. Voyager 2, traveling in a different direction, will pass near the star Ross 248 in about 42,000 years, coming within about 1.7 light-years. Again, this is not a close approach in any meaningful sense, just the spacecraft's first near pass of another stellar system. Over millions of years, the Voyagers will wander the galaxy. Without course corrections, their paths will be bent by the gravity of passing stars, by the overall gravitational field of the Milky Way. They might eventually be pulled toward the galactic center, or they might be flung to the outer reaches of the galaxy. Computer simulations suggest they'll likely remain in the galaxy for billions of years, possibly until the galaxy itself is disrupted by its eventual collision with the Andromeda Galaxy several billion years hence. Through all of this, the golden records will remain attached to the spacecraft, protected in their aluminum jackets. The records are made of gold-plated copper, materials chosen for their resistance to corrosion and degradation. In the vacuum of space, with no oxygen, no water, no biological organisms to cause decay, the records should remain playable for billions of years. Any civilization that eventually finds one of the Voyagers and figures out how to play the record will receive a message from Earth as it was in 1977. They'll hear our music, see our images, listen to our greetings in 55 languages. They'll get a snapshot of a small blue world orbiting an average star, a world that had developed a technological civilization curious enough to send this message into the cosmos. The odds of the Voyagers being found are vanishingly small. Space is vast, and the spacecraft are tiny. Even if intelligent civilizations are common in the galaxy, the chances that one of them will happen to pass close enough to a Voyager to detect it are minute. The golden records are less a serious attempt at communication with aliens, and more a message to ourselves, a statement that we exist, that we create, that we wonder about our place in the universe. But the possibility remains. Billions of years from now, long after the sun has died and Earth has been consumed or rendered uninhabitable, the Voyagers will still be out there, carrying their golden records, bearing witness to a civilization that once was. In that sense, the Voyagers are our ambassadors to eternity, proof that we existed, that we reached for the stars, that we dared to send a part of ourselves into the infinite, legacy and future. The Voyager missions have left an indelible mark on human understanding of the cosmos and on our sense of what is possible. When they were launched in 1977, no one could have predicted they would still be functioning nearly 50 years later, still making discoveries in regions of space no previous mission had reached. Yet here they are, in early 2026, continuing to transmit data from interstellar space, adding to a legacy that grows richer with each passing year. As of now, Voyager 1 is approximately 25 billion kilometers from Earth, or 166 astronomical units. The light travel time from Voyager 1 to Earth is about 23 hours, meaning when mission controllers receive a signal from the spacecraft, it left the spacecraft nearly a full day earlier. Voyager 2, though launched first, is traveling slightly slower and is currently about 21 billion kilometers away, or 140 astronomical units. Both spacecraft are the most distant human-made objects in existence. No other probe, satellite, or piece of space debris has traveled as far. They hold this record not because they're particularly fast, but because they've been traveling for so long. Persistence, in this case, has been more important than speed. The scientific papers based on Voyager data continue to be published. Decades of data from the Planetary Encounters are still being analyzed, still yielding insights, and the data from the Heliosphere's boundaries and from interstellar space is so new, so unprecedented, that it will likely be studied for decades to come. Each dataset raises questions that lead to new studies, new models, new understandings. One particularly active area of research involves combining Voyager data with observations from other missions. The IBEX mission, launched in 2008, creates maps of the heliosphere by detecting energetic neutral atoms emitted from its boundaries. These maps provide a global view that complements the Voyager's local, in situ measurements. By comparing IBEX's global maps with Voyager's point measurements, scientists can test and refine models of the heliosphere's structure. Similarly, the Interstellar Mapping and Acceleration Probe, or IMAP, launched in 2025, continues and extends IBEX's observations with more advanced instruments. IMAP provides higher-resolution maps of the heliosphere and tracks how the boundaries change over time, particularly as we move through different phases of the solar cycle. There are also proposals for future missions that could follow in the Voyager's footsteps, venturing beyond the Heliopause to explore interstellar space. An interstellar probe mission has been studied extensively, with concepts for a spacecraft that could reach 1,000 astronomical units in 50 years, far exceeding Voyager's distance and speed. Such a mission could carry modern instruments specifically designed to study the interstellar medium, the heliosphere's global structure, and the nearby regions of our galactic neighborhood. The challenges for such a mission are substantial. Reaching high speeds requires either very powerful rockets or advanced propulsion technologies like solar sails or nuclear electric propulsion. Maintaining communication over such vast distances requires large antennae and powerful transmitters. And the mission would need a power source that could last for decades. The RTGs used on Voyager are still the best option for the outer solar system and beyond, but supplies of plutonium-238 are limited, and producing more is expensive and complex. Despite these challenges, the scientific case for an interstellar probe is compelling. The Voyagers have shown us that the boundaries of the Heliosphere and the nature of the local interstellar medium are full of surprises. A dedicated interstellar mission could answer questions the Voyagers have raised, explore regions they cannot reach, and make measurements they cannot make with their 1970s-era instruments. Beyond the specific science, the Voyagers have had a profound cultural impact. The pale blue dot photograph, showing Earth as a tiny speck against the vastness of space, has become one of the most iconic images of the space age. Carl Sagan's reflections on that image, his meditation on our planet's fragility and preciousness, have resonated with millions of people around the world. The golden records, too, have captured public imagination. The idea that we have sent a message to potential alien civilizations, a collection of sounds and images representing humanity, is both humbling and inspiring. It speaks to a fundamental human need to connect, to share, to say, "We are here" to the universe. The Golden Record Project has been celebrated in books, documentaries, and even in a vinyl reissue released in 2017 for the mission's 40th anniversary, allowing people on Earth to own and listen to the same music that is traveling through interstellar space. The Voyagers have also inspired generations of scientists and engineers. Many of the researchers working on the mission today were not even born when the spacecraft launched. They grew up hearing stories of Voyager's discoveries, seeing the stunning images of Jupiter's swirling clouds and Saturn's intricate rings. For them, Voyager represents the enduring power of exploration, the rewards of pushing the boundaries of human knowledge. The spacecraft themselves have become symbols of human achievement and aspiration. They represent our ability to build machines that can function for decades in the harshness of space, our capacity to solve complex problems, our drive to explore beyond the familiar. In a very real sense, the Voyagers embody the best of what we can be: curious, creative, determined, and hopeful. As we look to the future, the Voyagers remind us of the value of long-term thinking and commitment. These missions succeeded because people in the 1970s made decisions that would benefit people decades later. They built spacecraft robust enough to last. They designed power systems that could function for much longer than the planned mission lifetime. And they created a ground system that could track and communicate with the spacecraft as they traveled to unprecedented distances. This kind of long-term planning is increasingly important as we face challenges like climate change and planetary sustainability. The Voyagers show us that we can undertake projects that span generations, that benefit people far in the future, if we're willing to commit to them. The missions also highlight the importance of international cooperation and the peaceful use of space. The Voyagers were NASA missions, but their data has been shared with scientists around the world. The discoveries they've made belong to all humanity, not to any single nation. The Golden Records explicitly present Earth as a single world, with greetings in many languages and music from many cultures, emphasizing our common humanity. As the Voyagers continue their journey into the 2030s and approach the end of their operational lives, we can look back on their accomplishments with pride and forward to the new missions they've inspired with anticipation. They've shown us the outer planets in detail, revealing worlds of astonishing beauty and complexity. They've mapped the boundaries of our solar system's protective bubble, the Heliosphere, and ventured beyond it into interstellar space. They've carried a message from Earth into the cosmos, a gesture of hope and connection that will endure for billions of years. When the last signals from Voyager 1 and Voyager 2 finally fade, when the power levels drop below the threshold needed for transmission, it will mark the end of an era. But it will not be the end of the Voyagers' story. They'll continue sailing through the galaxy, silent but enduring. Monuments to human curiosity and the courage to explore the unknown. And somewhere on Earth, in archives and institutions, the data they returned will continue to be studied, analyzed, and marveled at, a gift from the past to all the generations to come. Conclusion. As you lie here now, breathing slowly and deeply, let your mind drift along with the Voyagers, those lonely travelers moving through the darkness between the stars. Imagine them there, so far from Earth that our entire planet, our moon, our sun, all of it would appear as nothing more than a faint point of light, barely distinguishable from the countless other stars scattered across the black canvas of space. Feel the silence of that journey, the absolute stillness, the patient progression through a realm where time stretches out in scales almost incomprehensible to us. The Voyagers travel at 38,000 miles per hour, speeds that seem impossibly fast by our everyday standards. Yet, at those speeds it would take them tens of thousands of years just to reach the nearest neighboring star. Space is vast, more vast than we can truly grasp, and the Voyagers are teaching us to appreciate that vastness, to sit with it, to let it humble us and expand our perspective. Think about what these machines have shown us. They've revealed that the edge of our solar system is not empty, but filled with structure and complexity. Regions of hot plasma and magnetic turbulence. Boundaries that breathe and shift with the sun's activity. They have detected the hum of interstellar space itself, the quiet vibration of plasma between the stars, a sound that had never been heard before because nothing we'd built had ever been out there to listen. The Voyagers have measured temperatures hotter than the surface of the sun at the boundary, where solar wind meets galactic medium. Yet they've survived, protected by the emptiness of space itself, by the fact that even extreme temperatures mean little when there are too few particles to transfer that heat. They've shown us that our solar system has a shape, a structure, an interface with the galaxy that is dynamic and alive with physical processes we're only beginning to understand. And, perhaps most profoundly, the Voyagers have given us a new perspective on our place in the cosmos. They've shown us that we're not isolated, but embedded in a galaxy full of structure and energy, that our sun's influence extends billions of kilometers, but eventually must yield to the larger forces of the galaxy itself. They've demonstrated that boundaries in space are not walls, but transition zones, regions where different domains interact and exchange energy and matter. As you drift toward sleep, let yourself feel connected to this vast cosmos, to the journey of the Voyagers, to the long history of human exploration that brought us from huddling around fires on the African savanna to sending our machines into interstellar space. We are children of the cosmos, made of star stuff as Carl Sagan reminded us, and our curiosity, our drive to explore and understand, is as much a part of nature as the formation of galaxies or the evolution of stars. The Voyagers will continue their silent journey long after we're gone, carrying, with them, the golden records, those time capsules of Earth in 1977, bearing witness to a civilization that looked up at the stars and wondered, and then built machines to go there and see for ourselves. In the grandest sense, the Voyagers are us, our ambassadors to the future and to whatever or whoever might someday find them drifting through the galaxy. Let this thought bring you comfort as you settle into sleep. Somewhere out there, moving through the darkness at 38,000 miles per hour, two small spacecraft carry a message from all of us, a greeting, a gesture of hope and friendship cast into the cosmic ocean. They speak for Earth, for humanity, for the dream that we might one day take our place among the stars. Rest now, knowing that the journey continues, that the exploration goes on, that even as you sleep, the Voyagers are still out there, still traveling, still carrying our message into the infinite. The universe is vast and wondrous, full of mysteries we've only begun to uncover, and tomorrow, when you wake, there will be new discoveries waiting, new insights gained from these tireless explorers at the edge of everything we call home. Sleep well, dream of distant stars, and know that we've touched the realm beyond our sun, and in doing so, we've taken one small step toward understanding the great cosmic sea in which we all drift together. If you found peace and wonder in this journey through the cosmos, I'd be grateful if you would like this video and subscribe to the Science Pillow for more explorations designed to calm your mind and ease you into restful sleep. Your support means everything and helps this channel continue bringing you stories of science and space that comfort and inspire. Until next time, may your dreams be filled with the beauty of the universe.